Uh, Good morning, students. Today topic is specific heat capacity of the gas. Specific heat capacity of the gas. முக்கியமான 2 மார்க் கொஸ்டினுக்குன்னா 2 மார்க்கில் கேட்பாங்க 3 மார்க்கில் கேட்பாங்க. இப்போ என்னென்னு பார்த்தீங்கன்னா முன்னாடி நம்ம பார்த்துருக்கோம் the specific heat capacity of the gas very important role to determine the heat. To determine heat. எதை பேஸ் பண்ணி structure and molecular nature of structure and molecular nature of the system. So நமக்கு system அப்படின்னா என்னன்னு தெரியும் இல்லையா? Before that we are discussed. So that unlike solid, liquid, gas have two specific specific heat capacity of the constant என்னன்னு சொல்றீங்க SP அப்படின்னு சொல்றீங்க. And then specific heat capacity in a constant volume S இந்த ரெண்டு கான்ஸ்டன்ட் எடுத்துக்கிறீங்க. Specific heat capacity and specific heat capacity of the constant volume. Next, specific heat capacity at a constant pressure. At constant pressure. See, let us consider a container filled with gas. இப்போ கேஸ் இருக்கு, இங்கே ஒரு பிஸ்டன் வைக்கிறீங்க, இந்த பிஸ்டன்ல ஒரு மாஸ் பர்டிகுலர் மாஸ் இப்படி வைக்கும்போது amount of heat energy required to raise the temperature 1 kilogram அப்போ 1 Kelvin 1 degree Celsiusல என்ன இதான் நம்ம பார்க்க போறோம். Keeping a pressure at a constant is called specific heat capacity at a constant pressure. அப்போ என்ன பண்றோம்? At constant pressure. So constant pressure, the process of heat energy is used to doing the work. Remaining is increase the internal energy of the gas. இது என்ன ஆகும்? internal energy ஆட்டோமேட்டிக்காக இன்க்ரீஸ் ஆகுமா? ஸோ இன்டர்னல் எனர்ஜி இன்க்ரீஸ் ஆகும்போது என்ன ஆகும்? இங்கே நம்ம டெம்பரேச்சர் கொடுக்குறோம். இப்போ ஒரு டெம்பரேச்சர் கொடுக்குறீங்க அப்படின்னா ஆட்டோமேட்டிக்காக மாஸ் என்ன ஆகும்? இங்கே ப்ரெஷரும் வரும் த சேம் டைம். ஸோ ஸ்பெசிஃபிக் ஹீட் கெப்பாசிட்டி அட் அ கான்ஸ்டன்ட் வேல்யூம். அப்போ கான்ஸ்டன்ட் வேல்யூம் அப்படின்னா என்ன அர்த்தம்? எஸ் வி ஸோ இதுக்கு என்ன அர்த்தம்? 1 Kelvin ஆர் 1 degree Celsius இன்க்ரீஸ் பண்ணுறதுக்கு 1 Kelvin degree Celsius increase பண்றதுக்கு keeping the volume at a constant is called the specific heat capacity at a constant volume. If the volume kept constant, then the supplied is used to increase only the internal energy. No work done is gas. அப்போ work done என்ன ஆகுது? இங்க மாறுது. So it is impulse that temperature of the gas at a constant volume it's required to less the heat இங்க heat நம்ம reduce பண்றோம். So heat will be reduced, then the temperature of the gas constant pressure. So இதுதான் என்ன சொல்றீங்க அப்படின்னா specific heat capacity. அடுத்தது molar specific heat capacity. Molar specific heat capacity. It is sometimes it is useful to calculate the molar heat capacity Cp and Cv and pressure and volume. The amount of heat required to temperature of the 1 mole, the substance is 1 kilo Kelvin 1 degree Celsius. So that at a constant volume pressure, if the pressure is kept constant, இப்போ pressure என்ன பண்றீங்க அப்படின்னா கான்ஸ்டன்டா வைக்கிறீங்க. So pressure is constant, then the specific heat capacity of the constant of the pressure இங்க என்ன ஆகுது அப்படின்னா, so pressure constant வைக்கும்போது Q அப்போ amount of heat Q என்ன ஆயிரும், Q equal to mu C del T. இப்படி கிடைக்குமா? அதாவது heat supplied the mole of the gas at a constant and the temperature change in the amount. அப்போ இதை என்ன சொல்றாங்க, change in the temperature, change in temperature del T. So இப்போ dV equal to 0 அப்படின்னு calculate பண்றீங்க அப்படின்னா dV equal to 0 அப்படின்னு எடுத்துக்கிட்டா Q equal to என்ன ஆயிரும், Q equal to del U minus 0. So del U, next we can calculate del U. So del U equal to என்ன எழுதுறீங்க அப்படின்னா mu CV del T. Okay, here CV equal to எப்படி எழுதலாம், 1 by mu del U by del T. So the limit of del T is 0, then CV equal to 1 mu இப்போ differentiate பண்றீங்க du by dt. இதுதான் நமக்கு கிடைக்கக்கூடிய final value. Okay, so specific heat capacity of the, to determine the structure and molecular structure, specific heat capacity at a constant pressure, இதுதான் நம்ம கன்சிடர் பண்றோம். Next, Mayer's relation.
And welcome to High School Physics Explained, and today I want to talk about specific heat capacity. So you're making a pizza, you've got a base, you've got tomato base, you've got cheese and bacon, and you put it in an oven at 200 degrees Celsius. Which of those substances will reach 200 degrees first? Well, that of course depends on A, the amount of each of those substances you have, and B, on the type of substance, and that is related to the specific heat capacity. To help us understand, let's have a look at this specific illustration. I have a beaker here of water, and underneath it I place a Bunsen burner with gas, and so of course energy is going to be transferred from the flame into the water. How much energy will I require if I want to raise it by 1 degree? Well, of course, that will depend on the amount of liquid. So I'm going to require more energy if I have more liquid. But if I have a beaker, let's say, of oil, and let's say it's the same volume as our first beaker, then I'm going to probably need less energy to raise it by 1 degree, simply by the fact that I have not got water here, but I've got oil. And if I have the same amount of, let's say, a bar of iron, I'm going to probably need a lot less energy to raise this to a temperature by 1 degree. So in essence, that's what the specific heat capacity is. It's the amount of energy supplied or removed to change 1 kilogram of that substance by 1 degree. So it's going to be the same if we ignore the amount here, and that's why we've got 1 kilogram here. So let's summarize that. So what do we need? We want the amount of energy, and we're going to call that Q. We want to raise it by 1 degree, so we're going to have amount of energy per degree or per amount of temperature, and of course per kilogram, so we're interested in dividing it per unit mass. And so that becomes the value C, which is called our specific heat capacity. If I rearrange that formula, I get this formula. Q equals Cm delta T. That is, the amount of energy is equal to the specific heat capacity of my substance multiplied by the mass of my substance multiplied by the temperature. And so what we have here is a table of specific heat capacities. And what we're interested in here is this particular column here, because this is the correct SI unit. And you can see various substances have specific heat capacities. Some substances have fairly low specific capacities, 450 joules per kilogram per degree Celsius for iron, something significantly higher for water at the liquid state at 4,186. So if we go back to our illustration here, the specific heat capacity for water is 4182. The specific heat capacity for oil is 1670, and the specific heat capacity is 450. What does that mean? I need a lot more energy to raise this substance for every kilogram I have by 1 degree than I do for oil. And you can see that iron doesn't need a lot of energy to raise it to 1 degree. Similarly speaking, if I want this to drop a certain amount of it, let's say a degree, it's going to release only 450 joules. If I want this to drop by a degree, I'm going to release significantly more energy, 4,182 joules for every kilogram. How does that play out though in everyday sense? So let's look at 2 examples that gives you hopefully a better understanding of specific heat capacity, and in particular we're going to look at water. Well, water is used of course as a coolant in engines. Why is that? Well, water has a fairly high specific heat capacity, 4,182 joules per kilogram per degree Celsius. Now, of course, in a radiator, you may have, let's say, 5 litres. So therefore we have a mass of around 5 kilograms of water. Finally, we want the temperature to go from, let's say, 20 degrees, and we only want it to get to, let's say, 100 degrees. Why? Because we don't want it to go into a gaseous state. Now, because it's under pressure, we probably can go to a higher temperature here. But just for this example, let's say we only want an 80 degree change. Then the amount of energy required is going to be 4,182 multiplied by 5 multiplied by my change in temperature, which is going to be 80 degrees. And that is equal to 1,672,800 joules. That's a lot of energy. And that, of course, is going to be taken away from the engine. And so that's why water is used as a coolant. It can actually take a lot of energy before going into the gaseous state. So let's have a look at another example where water having a high specific heat capacity has an impact on us. So here we have the continent of Australia, and we have a certain amount of energy falling on, per square meter, the same whether it's on the land, on the coast, or over water. Remember, water has a high heat capacity, and so if you were to compare the temperature increases over the water and over the land, considering that they're all receiving the same amount of energy, which one will increase the temperature the greatest? Well, it's going to be much greater on the land because it has a lower heat capacity. And so therefore, with the same amount of energy, since water has a high heat capacity, it is only going to increase by a small amount in terms of temperature. Whereas the land, having a lower heat capacity for the same amount of energy, will have a much greater increase in temperature. which means, for example, in summer, it's going to generally be cooler on the coastline than inland, simply because you're going to have this temperature increasing on the surface, and that, of course, is going to heat up the air above it. But what about in winter? Well, in winter, of course, it's going to be significantly cooler than the surrounding, and so what we're going to get is that the water will start to cool, but because of its high heat capacity, it's going to not necessarily drop in temperature too quickly. It's going to have a lower temperature drop, and so as a result, you're going to get a small drop in temperature, and so generally speaking, you're going to get water that is not going to be significantly colder in winter than if you compare it to the land situation. Again, a low heat capacity means the temperature will drop more quickly, more significantly, and therefore it's going to be colder. In other words, inland you're going to get extremes in temperature, whereas on the coasts you're not going to get as many extremes. Again, all has to do with the concept of specific heat capacity. Finally, let's have a look at an example where we use this formula. Let's say cold water is at 15 degrees and it enters a heater, and the resulting temperature you use is at 61 degrees. Now, assuming a person uses 120 kilograms of water, how much energy is needed to heat this water? Well, you need this formula. Q is equal to Cm delta T. Q, of course, is what we're after, so we'll write this down. Unknown. Our specific heat capacity is 4,182 joules per kilogram per degree Celsius. Our mass in this case is equal to 120 kilograms, and our change in temperature, our delta T, is the difference, that is 61 minus 15, which is equal to 46 degrees. And so therefore 4182 multiplied by 120 multiplied by our change in temperature, which is 46 degrees, gives us a grand total of 2.3 by 10 to the power of 7 joules. That's how much energy is gone into the water. Now, all of these situations that we're talking about here deal with substances that aren't changing state at all. So the energy putting in does not change whether a substance goes from solid to liquid to gas or any other way. That requires an understanding of latent heat, and that will be the topic of our next video. I'm Paul from High School Physics Explained. I hope this has helped you. Please like, share and subscribe. Bye for now.
Good evening. Next topic என்னன்னு பார்த்தீங்கன்னா Mayer's relation. Mayer's relation. Important 5-mark question kana. So you consider mu is a molecular. Mu is equal mu mole of an ideal gas constant with the volume. அப்போ வால்யூம் V அப்படின்னு எடுத்துக்கிறீங்க. Volume V. Next, P is a temperature and T is a temperature. P is a pressure. T is temperature of the ideal gas. Temperature of the ideal gas. இப்போ நமக்கு ஆல்ரெடி நம்ம முன்னாடி பார்த்தது என்னன்னா gas relationshipல பார்த்திருப்போம் du. If Cs is the molar specific heat capacity at a constant, இப்போ du equal to mu Cv dt அப்படின்னு கன்சிடர் பண்றீங்க அப்படின்னா, so suppose the heat is constant pressure, so that pressure will be increased by dt. இப்போ ப்ரெஷர் இன்க்ரீஸ் ஆகுறதுனால டிடியும் இன்க்ரீஸ் ஆகுது அப்படின்னு நீங்கள் கன்சிடர் பண்ணுறீங்க அப்படின்னா, Cv in the heat supplied, the process dV is volume of the gas. அப்போ Q equal to என்ன எழுதலாம்? Q equal to mu constant pressure and then dt. இப்படி எழுதலாமா? ஸோ W is work done அப்படின்னு எடுத்துக்கிட்டீங்க அப்படின்னா நமக்கு W என்னன்னு தெரியும், work done அப்படின்னு கன்சிடர் பண்றீங்க. W is work done. So Q equal to Cp dt. அப்போ W is work done by the process. அப்போ இந்த ப்ராசஸில் நடக்கும்போது W equal to என்ன எழுதலாம், P dV. So the first law of thermodynamics நமக்கு என்ன தெரியும், first law of thermodynamics Q equal to du plus W அப்படி எழுதலாமா? ஸோ இந்த டபிள்யூவோட வேல்யூ இங்கே சப்ளை பண்ணுங்க. அப்போ என்ன ஆகும், கியூவோட வேல்யூ u cp dt ஈக்குவல் டு மியூ சி, இங்கே என்ன ஆகும், வேல்யூம் கான்ஸ்டன்ட் dt ப்ளஸ் pdv இல்லையா? ஸோ மோல் ஆஃப் ஐடியல் கேஸ், இப்போ மோல் ஆஃப் ஐடியல் கேஸ், ideal gas இதை நம்ம கன்சிடர் பண்ணுறோம். PV equal to mu RT. PV equal to mu RT. PV equal to mu RTங்கிறது நமக்கு தெரியும். ஸோ mu RTயில் இது எப்படி எழுதலாம், P dV, ஏன்னா ப்ரெஷர் வேல்யூம் ரெண்டுமே இருக்கும். அப்புறம் வேல்யூம் dP, இது ரெண்டையும் வித் ரெஸ்பெக்டடாக வச்சுக்கிட்டு இஸ் ஈக்குவல் டு எதுக்கு ஈக்குவலாக இருக்கும், மியூ ஆர் டிடிக்கு ஈக்குவலாக இருக்கும். ஸோ ப்ரெஷர் இஸ் கான்ஸ்டன்ட், இங்கே ப்ரெஷர் இஸ் கான்ஸ்டன்ட். ப்ரெஷரை கான்ஸ்டண்ட்டாக வைக்கும்போது ஆட்டோமேட்டிக்காக என்ன ஆகும், சிபி டிடி ஈக்குவல் டு எப்படி எழுதலைங்க, சிவி டிடி ப்ளஸ் ஆர் டிடி, பிகாஸ் டிபி ஈக்குவல் டு 0 அப்படின்னு கன்சிடர் பண்ணுறீங்க அப்படின்னா, ஸோ சிபி along the pressure is equal to CV plus R. இப்படி எழுதலாம், CP minus CV equal to R. இப்படியும் நம்ம எழுதலாம். So it is that impulse that the capacity of the ideal gas at a constant pressure is greater than molecular specific heat capacity, a constant volume. The relation shows that specific heat capacity of the constant pressure is always greater than specific heat capacity of the constant volume. So இதுதான் நம்ம சொல்றோம். Next, thermodynamic process.